Most of our planet is a world almost no one has ever seen. Deep, dark, and cold. A place where pressure can crush steel. Where strange creatures glow with their own light. Where entire ecosystems thrive without a single ray of sunlight. My name is Atta. This is the Quiet Observatory. Tonight, we're descending into that world, into the deep sea, the dark ocean that covers most of Earth's surface, holds most of its water, and remains almost entirely unexplored. You could sail a boat across it. You could swim in its uppermost layers. But venture down just a few hundred meters, and you enter a realm stranger and less familiar to us than the far side of the moon. When we say deep sea, we mean the ocean below about 200 meters, the depth where sunlight fades to darkness. And this zone encompasses over 95% of the ocean's volume. The vast majority of Earth's oceans are deep, dark, cold, and largely unexplored. We've mapped more of the moon's surface than we have of the ocean floor. We've sent more people into space than to the deepest parts of the ocean. We know more about the surface of Mars than we know about the abyssal plains that cover much of our own planet. Tonight, we're descending into this hidden world. We'll journey from the sunlit surface down through layers of increasing darkness and pressure, meeting strange life forms adapted to extremes we can barely imagine. We'll explore the ocean floor, where hot springs support ecosystems that don't depend on sunlight. And we'll visit the deepest place on Earth, the Mariana Trench, where the pressure is over 1,000 times greater than at sea level. And yet, life persists. Let's begin our descent at the surface, where light still penetrates, and move slowly downward into the abyss. The ocean isn't uniform. It's stratified into distinct zones, each with its own characteristics, its own community of life, its own challenges and opportunities. Let's descend slowly, noticing how the world changes with depth. The sunlight zone, or epipelagic zone, extends from the surface down to about 200 meters. This is the ocean most people know, the realm of swimming, diving, coral reefs, and kelp forests. Sunlight penetrates this zone, allowing photosynthesis. Phytoplankton, microscopic algae, drift near the surface, forming the base of the ocean food web. Most marine life lives here. Fish schools, dolphins, sea turtles, sharks, whales passing through, all depend directly or indirectly on the sunlight that powers photosynthesis. Coral reefs, among the most biodiverse ecosystems on Earth, thrive in shallow tropical waters where light is abundant and warm. The sunlight zone is bright, warm in the tropics, teeming with life. But we're descending, and as we pass 50 meters, 100 meters, 150 meters, the light is fading. Colors disappear, one by one. Red first, absorbed by the water, then orange, then yellow. By 200 meters, only blue light remains, dim and ghostly. At 200 meters, we enter the twilight zone, or mesopelagic zone, extending from 200 to 1,000 meters deep. Here, there's still some light, enough to see vague shapes, but not enough for photosynthesis. It's a world of perpetual dusk, where the faint glow from above provides just enough illumination to hunt or hide. And an astonishing thing happens here every night. The largest migration of animals on Earth. Every evening, billions of fish, squid, jellyfish, and krill rise from the twilight zone toward the surface to feed. Every morning, they descend back down to the safety of the deep. This vertical migration happens daily in oceans around the world, involving more biomass than all of humanity. Why do they migrate? At the surface, there's food, the phytoplankton that bloom in sunlight. But there are also predators that hunt by sight. By ascending only at night, when it's dark, the migrators reduce their risk while accessing the abundant food near the surface. In the twilight zone, bioluminescence becomes common. Many creatures here glow, producing their own light through chemical reactions. Some use it to attract prey. Some use it to confuse predators. Some use it to communicate with potential mates. The water is cooler here, around 5 to 10 degrees Celsius. The pressure is increasing, but still manageable for human-made submersibles. We continue descending. The last traces of sunlight fade completely. At 1,000 meters, we enter the midnight zone, or bathypelagic zone, extending from 1,000 to 4,000 meters. Here, there is no sunlight at all. It's completely dark, except for the eerie glow of bioluminescent creatures. The temperature hovers around 2 to 4 degrees Celsius, just above freezing. The pressure is now about 100 times atmospheric pressure at the surface, enough to crush most human-made objects not specifically designed to withstand it. Life is sparse here, but it's present. Fish with huge eyes, adapted to detect faint bioluminescence. Others with no eyes at all, relying entirely on other senses. Gelatinous creatures, jellyfish, siphonophores, comb jellies, drift through the darkness, some trailing tentacles dozens of meters long. Food is scarce in the midnight zone. There's no photosynthesis, so the only food comes from above. Dead organisms sinking from the surface. A slow rain of organic matter called marine snow. Everything down here is part of a scavenging economy. waiting for food to fall from the lit world above. Below 4,000 meters, we reach the abyssal zone, or abysso-pelagic zone, extending from 4,000 to 6,000 meters. The abyss. The word itself evokes darkness, depth, the unknown. The abyssal plains are vast, flat expanses, covering much of the ocean floor. The temperature is near freezing, just a degree or two above 0 Celsius. The pressure exceeds 400 atmospheres, more than 400 times the pressure at sea level. If you could somehow survive here without protection, the pressure would compress your body, forcing air out of your lungs, collapsing your chest cavity. And yet, life exists. Sea cucumbers crawl across the seafloor, feeding on sediment. Brittle stars wave their arms, filtering particles from the water. Fish with soft, gelatinous bodies drift in the current. Amphipods, shrimp-like crustaceans, scuttle across the mud. The abyss is not lifeless. It's just quiet, slow, energy poor. Every calorie counts in this dark, cold desert. But we're not at the bottom yet. We're going deeper still. At 6,000 meters, we enter the hadal zone, or hadopelagic zone, extending from 6,000 meters down to the deepest point in the ocean, at nearly 11,000 meters. The hadal zone exists only in ocean trenches, long, narrow chasms in the seafloor, where tectonic plates collide, and one plate is forced beneath the other in a process called subduction. The Mariana Trench, the Tonga Trench, the Philippine Trench, the Peru-Chile Trench, all are hadal environments. The name comes from Hades, the Greek underworld, and it's fitting. These trenches are the deepest, darkest, most extreme environments on Earth. At the bottom of the Mariana Trench, Challenger Deep, the deepest known point, the depth is 10,994 meters. The pressure is 1,086 atmospheres, or over 15,000 pounds per square inch. That's like having 50 jumbo jets stacked on top of a postage stamp. At this depth, water itself behaves differently. It's denser, more viscous. Gas bubbles don't rise. They're compressed too much by the pressure. Styrofoam cups, if lowered to this depth, are compressed to a fraction of their original size, crushed by the sheer weight of the water above. And yet, astonishingly, life exists even here. We'll return to the Mariana Trench shortly. For now, let's pause at a comfortable depth, say 2,000 meters, deep in the midnight zone, and ask, how does anything live in these conditions? The deep sea seems hostile to life. No light, freezing temperatures, crushing pressure, scarce food. And yet, life has found a way. Evolution has crafted organisms exquisitely adapted to these extremes, with solutions so elegant and strange, they seem almost alien. Let's start with the most visible adaptation: bioluminescence. In the deep sea, where sunlight never reaches, about 90% of organisms produce their own light. Bioluminescence is not rare in the deep. It's the norm. The chemistry is relatively simple. A molecule called luciferin reacts with oxygen in the presence of an enzyme called luciferase, releasing energy as light. Different species use slightly different variants of these molecules, producing different colors and intensities of light. The uses of bioluminescence are diverse and ingenious. Flashlight fish carry bioluminescent bacteria in light organs beneath their eyes. They can control the light by raising or lowering a skin flap over the organs, flashing the light on and off. They use this to communicate with each other, to coordinate schooling behavior at night. Vampire squid, despite the name, not a true squid, can eject a cloud of bioluminescent mucus when threatened. The glowing cloud confuses predators, giving the vampire squid time to escape into the darkness. It's like a squid's ink cloud, but made of light instead of pigment. Hatchetfish and many other midwater fish have light organs on their undersides. They emit a dim glow that matches the faint downwelling light from above, making them nearly invisible to predators looking up from below. This is called counter-illumination camouflage, hiding by producing the right amount of light to blend with the background. Some organisms use bioluminescence to communicate. Fireflies on land do this, flashing patterns to attract mates. Deep-sea species may do the same, though we've observed it less directly. Certain species of squid flash and pulse in complex patterns that might be visual language. Others use it defensively. Some jellyfish and plankton emit bright flashes when disturbed, a behavior called the burglar alarm. The flash attracts larger predators, which may attack and eat the original attacker, inadvertently saving the flasher. But bioluminescence is just one adaptation. Let's consider pressure. At the surface, we experience 1 atmosphere of pressure, the weight of all the air above us. At 1,000 meters deep, the pressure is 100 atmospheres. At 10,000 meters, over 1,000 atmospheres. How do deep-sea organisms survive this crushing force? The key is that they have no air spaces in their bodies. Gas compresses under pressure. Air-filled lungs or swim bladders would collapse, but water is incompressible, and so is most biological tissue. If an organism's body is filled with water, muscle, fat, and gelatinous tissue, all incompressible, the external pressure is balanced by internal pressure, and the organism is not crushed. Deep-sea fish often have soft, gelatinous bones rather than hard, mineralized ones. Their bodies are less dense, more flexible. Some look almost ghostly, translucent, with fragile fins and minimal musculature. Their proteins are adapted to function under high pressure. At the molecular level, pressure affects how proteins fold and function. Deep-sea species have evolved specialized proteins that remain stable and functional under conditions that would denature the proteins of surface species. Interestingly, if you bring a deep-sea organism to the surface too quickly, it doesn't necessarily explode as depicted in movies, but it can suffer from rapid decompression. Dissolved gases in its tissues expand, sometimes causing damage, and organisms adapted to high pressure and low temperature may not function well at the surface, even if their bodies remain intact. Food scarcity is another major challenge. In the deep sea, food is rare. There's no photosynthesis, so no primary production. The only food sources are 1. Marine snow, dead plankton, fecal pellets, and organic debris sinking from the sunlit layers above. This rain of detritus is the primary food supply for most deep sea life. And 2. Occasional bonanzas, the carcass of a whale or large fish that sinks to the seafloor and provides a massive localized food source for months or years. Deep-sea organisms have adapted to this scarcity with slow metabolisms. They grow slowly, reproduce infrequently, and live long lives. Some deep-sea fish can live for decades, growing just millimeters per year. Their senses have adapted as well. Vision is problematic in the deep. There's no sunlight, and bioluminescence is dim and sporadic. Some fish have enormous eyes, often upward facing, to catch every photon of available light. The eyes may be tubular, almost telescope-like, sacrificing peripheral vision for sensitivity. Other species have abandoned vision entirely. Some fish have no eyes at all, or only vestigial, non-functional eyes. Instead, they rely on other senses. The lateral line system, a row of sensors along a fish's body that detects vibrations and pressure changes in the water, becomes crucial. Deep-sea fish can sense the movement of prey or predators by the disturbances they create, hunting in complete darkness. Chemical senses, smell and taste, are also enhanced. Many deep-sea species have elongated sensory barbels or filaments that detect chemical traces in the water. There's one more adaptation worth mentioning: deep-sea gigantism. Many deep-sea species grow much larger than their shallow water relatives. Giant squid, giant isopods, giant amphipods, Japanese spider crabs with leg spans exceeding 4 meters. The reasons are debated. Cold temperatures slow metabolism, which may allow organisms to grow larger and live longer. Food scarcity favors larger body size because larger organisms can survive longer between meals and travel farther to find food. And in the deep, there are fewer predators, reducing the evolutionary pressure to stay small and agile. Whatever the reasons, the deep sea is home to some of Earth's largest invertebrates and strangest giants. In 1977, a team of geologists and biologists descended to the seafloor near the Galapagos Islands in the submersible Alvin. They were exploring the mid-ocean ridge, the longest mountain range on Earth, which runs along the floor of the world's oceans, where tectonic plates are spreading apart. They expected to find a barren landscape, cold, dark, lifeless. What they found instead would revolutionize biology. Hydrothermal vents, underwater hot springs, where superheated water, rich in minerals and chemicals, gushes from cracks in the seafloor. The water emerging from these vents can reach temperatures of 400 degrees Celsius, hot enough to melt lead. It doesn't boil because of the immense pressure at depth. The water is black or white with dissolved minerals, hence the names black smokers or white smokers, that precipitate out when the hot water meets the cold seawater, forming chimney-like structures that can grow several stories tall. And surrounding these vents, thriving in conditions that should be toxic and lethal, were dense communities of life unlike anything seen before. Giant tube worms, Riftia pachyptila, up to 2 meters long, with bright red plumes extending from white tubes anchored to the rocks. Clusters of mussels and clams, strange pale crabs and shrimp, fish hovering in the warm water. This was impossible. The deep sea was supposed to be a desert, sustained only by the faint trickle of organic matter falling from the surface. Yet here was a lush ecosystem teeming with life in one of the most hostile environments on Earth. How? The answer lay in a process no one had seen in nature before: chemosynthesis. On the surface, nearly all ecosystems depend ultimately on photosynthesis, the process by which plants and algae use sunlight to convert carbon dioxide and water into sugars. Photosynthesis is the base of the food chain. Without it, there would be no primary production, no food, no complex ecosystems. But at hydrothermal vents, there's no sunlight. Instead, bacteria use chemical energy from the vent fluids. The vent water is rich in hydrogen sulfide, a chemical that's toxic to most life. But certain bacteria can oxidize hydrogen sulfide, extracting energy from the chemical reaction and using it to build organic molecules from carbon dioxide. This is chemosynthesis. These bacteria form the base of the vent food chain. Some live freely in the water. Others form dense mats on rocks, like bacterial lawns. And some live symbiotically inside other organisms. The giant tube worms, for instance, have no mouth and no digestive system. They cannot eat. Instead, they house chemosynthetic bacteria inside a specialized organ called a trophosome. The worm's red plumes absorb hydrogen sulfide and oxygen from the water, delivering them to the bacteria. The bacteria produce sugars, which the worm absorbs. It's a complete partnership. The worm provides the bacteria with raw materials, and the bacteria provide the worm with food. Other vent species have similar arrangements. Vent mussels and clams house bacteria in their gills. Vent shrimp carry bacteria on their backs or in their mouths. The discovery of chemosynthesis-based ecosystems was profound. It showed that life doesn't require sunlight. It can thrive on chemical energy alone. This has implications for the search for life elsewhere in the solar system. Europa, one of Jupiter's moons, has a global ocean beneath an icy shell. That ocean is far from the sun, receiving no sunlight. But Europa's core is likely still warm, and there may be hydrothermal vents on its seafloor. If vent ecosystems exist there, they could thrive without sunlight, just as they do on Earth. The same is true for Enceladus, Saturn's small icy moon, which has geysers spraying water from a subsurface ocean. That ocean likely has hydrothermal activity as well. Hydrothermal vents may represent one of the most ancient environments for life. Some scientists believe life on Earth originated at vents, where chemical energy was abundant, minerals provided raw materials, and the heat provided energy for chemical reactions. The vents are also remarkably diverse. Some are hot, others cooler. Some emit metal-rich fluids, others sulfur-rich. The chemistry varies, and different vent communities have evolved to exploit different chemical environments. Pompeii worms, for example, live in tubes built on the sides of black smoker chimneys, where temperatures can reach 80 degrees Celsius, among the highest temperatures tolerated by any animal. They're covered in a fleece of bacteria that may insulate them or provide food. Scaly foot snails have shells reinforced with iron sulfides, essentially armor made of metal. They're the only animals known to incorporate iron sulfides into their skeletons. Yeti crabs, discovered in 2005, have hairy claws covered in bacteria. They wave their claws in the vent flow, farming the bacteria, then scrape them off and eat them. Vent communities are also ephemeral. Vents don't last forever. Volcanic activity shifts, chimneys collapse, new vents open elsewhere. A vent might be active for just a few decades before going extinct. When a vent dies, the ecosystem dies with it. But vent species have adapted to this instability. Many have planktonic larvae that drift in ocean currents for weeks or months, allowing them to colonize new vents as they appear. There's a constant turnover. Old vents dying, new vents being colonized, a dynamic mosaic of life across the ocean floor. The discovery of hydrothermal vents in 1977 was one of the most important biological discoveries of the 20th century. It expanded our understanding of where life can exist, how ecosystems can function, and what to look for in the search for life beyond Earth. And there are still new vent systems being discovered, each with its own unique community, its own species found nowhere else. The deep ocean continues to surprise us. Now let's descend to the very deepest point on Earth, Challenger Deep in the Mariana Trench. The Mariana Trench is a crescent-shaped scar in the Pacific Ocean floor, stretching for over 2,500 kilometers. At its deepest point, Challenger Deep, the ocean is 10,994 meters deep, or nearly 11 kilometers. To put this in perspective, if you placed Mount Everest, the tallest mountain on Earth, at the bottom of Challenger Deep, its peak would still be over 2 kilometers underwater. The first humans to reach Challenger Deep were Jacques Piccard and Don Walsh, who descended in the bathyscaphe Trieste on January 23, 1960. The journey down took nearly 5 hours. They spent just 20 minutes at the bottom before beginning the ascent, which took over 3 hours. At the bottom, they saw something remarkable through the small porthole: a flatfish swimming and a shrimp. Life at the deepest point on Earth. This was astonishing. The pressure at Challenger Deep is 1,086 atmospheres, over 15,000 pounds per square inch. It was believed that no complex life could survive such pressure. But there it was. For over 50 years, Trieste's dive remained the only manned visit to Challenger Deep. Then, in 2012, filmmaker and explorer James Cameron descended alone in the submersible Deep-Sea Challenger. Cameron spent about 3 hours at the bottom, filming, collecting samples, and observing. He described the bottom as desolate, moon-like, with fine sediment and no large organisms visible. But his samples contained amphipods, shrimp-like creatures several centimeters long, and microbial life in the sediment. In 2019, Victor Vescovo, a private explorer, made multiple dives to Challenger Deep in the submersible DSV limiting factor, reaching a depth of 10,928 meters, slightly deeper than Cameron's dive. His team discovered several new species, including a type of snailfish that holds the record for the deepest fish ever recorded. But Vescovo also found something disturbing: a plastic bag and candy wrappers at the bottom of the trench. Human pollution has reached even the most remote, extreme environment on Earth. Nowhere is untouched. So what lives at Challenger Deep? The dominant animals are amphipods, small crustaceans related to shrimp. Some species are endemic to the hadal zone, found only in the deepest trenches. They're scavengers, feeding on organic matter that sinks to the bottom. Snailfish, soft-bodied, translucent fish, are the deepest living vertebrates. The Mariana snailfish, discovered in 2014, lives at depths between 6,000 and 8,000 meters. Below that, the pressure may be too great, even for fish to survive. Sea cucumbers, gelatinous echinoderms, crawl across the seafloor, feeding on sediment. Some species are found only in the hadal zone. And in the sediment itself, there are microbes, bacteria and archaea that survive the pressure and cold, feeding on whatever organic matter reaches the bottom. The pressure at Challenger Deep has profound effects on biochemistry. Proteins must be adapted to remain functional. Membranes must remain flexible despite being compressed. Even DNA can be affected by extreme pressure. Yet, life persists. Evolution has found solutions to every challenge the deep poses. It's worth noting that fewer people have visited Challenger Deep than have walked on the moon. Just 3 manned missions in over 60 years. The moon is, in some ways, more accessible than the bottom of our own ocean. This is partly because of the technical challenges. Submersibles must withstand enormous pressure, remain functional in freezing temperatures, and navigate in complete darkness. There's no GPS underwater. No radio signals penetrate the ocean. Navigation relies on sonar and inertial guidance systems. And there's little funding for deep-sea exploration compared to space exploration. The ocean is often overlooked, despite covering 70% of Earth's surface and containing most of the planet's habitable volume. But gradually, we're learning more. Robotic submersibles, remotely operated vehicles, ROVs, and autonomous underwater vehicles, AUVs, can reach depths humans cannot, staying down longer and collecting data continuously. Landers, unmanned platforms that sink to the seafloor, collect samples, and then drop weights to rise back to the surface, have been deployed to the deepest trenches, bringing back specimens and video footage. Each expedition reveals new species. Some estimates suggest there may be 1 million undiscovered species in the deep ocean, perhaps more. We've only begun to catalogue the biodiversity of the abyss. For all we've learned, the deep sea remains profoundly mysterious. There's so much we don't know, so many questions unanswered. The ocean covers 361 million square kilometers, and the average depth is about 3,700 meters. That's an immense volume, over 1.3 billion cubic kilometers, and most of it is deep sea. Yet, we've explored less than 10% of it. We've mapped perhaps 20% of the seafloor at high resolution. The rest is largely unknown. New species are discovered constantly. In 2021, scientists described the dusky dolphin incident, a phenomenon where bioluminescent waves appeared off the coast of California, caused by blooms of tiny plankton. Each expedition to the deep brings back creatures never seen before. The giant squid, Architeuthis, was one of the ocean's greatest mysteries for centuries. Tales of sea monsters and kraken may have been inspired by sightings of giant squid. They can grow to 13 meters in length, with eyes as large as dinner plates, the largest eyes in the animal kingdom. But despite being known from dead specimens washed ashore or caught in nets, no one had ever seen a living giant squid in its natural habitat until 2012, when Japanese researchers filmed one in the deep ocean off Japan. It was shy, elusive, moving gracefully through the darkness. Nothing like the aggressive monster of legend. The colossal squid, Mesonicoteuthis, is even larger, with a heavier body and longer tentacles equipped with rotating hooks. Specimens have been found in the stomachs of sperm whales, which hunt them at depth. But a living colossal squid has never been observed. What else is down there, in the dark, that we haven't seen yet? In 1997, a mysterious sound was detected by underwater microphones, hydrophones, deployed by NOAA in the Pacific Ocean. The sound, named the bloop, was one of the loudest underwater sounds ever recorded, It was low frequency, powerful, and unlike anything known. Speculation ran wild. Was it a giant unknown creature? A sea monster? Something enormous lurking in the abyss? The mystery was eventually solved. The bloop was an icequake, the sound of a large iceberg fracturing or calving from an ice shelf. But for years, it captured imaginations, a reminder of how much we don't know about the ocean. The deep sea is still a frontier. We've explored more of the moon's surface and the ocean floor. We've sent robots to Mars, but we've only visited Challenger Deep 3 times. There are entire mountain ranges underwater that have never been surveyed. Vast plains of sediment stretching for thousands of kilometers, unseen. Canyons deeper than the Grand Canyon, unexplored. And new technologies are changing what's possible. Autonomous underwater vehicles can map the seafloor, collect samples, and even discover new hydrothermal vents. Improved cameras and lighting allow us to film deep sea life without disturbing it. Environmental DNA sampling, analyzing DNA in seawater, can detect species without even seeing them. But there are threats to the deep sea as well. Climate change is warming the ocean, even at depth. The deep ocean acts as a heat sink, absorbing much of the excess heat trapped by greenhouse gases. This warming is gradual, but it's happening, and it will affect deep sea ecosystems. Ocean acidification, caused by the ocean absorbing carbon dioxide from the atmosphere, is changing the chemistry of seawater, making it harder for organisms to build shells and skeletons. This affects everything from plankton to corals to deep sea mollusks. Deep sea mining is being proposed and tested, extracting valuable minerals from the seafloor, particularly from hydrothermal vents and manganese nodules that cover the abyssal plains. The environmental impacts are uncertain, but they could be severe, destroying habitats before we've even fully studied them. Overfishing affects the deep as well. Deep sea trawling, dragging heavy nets across the seafloor, destroys benthic communities, scraping away corals, sponges, and other slow-growing organisms that may be centuries old. And plastic pollution, as we've seen, reaches even Challenger Deep. Microplastics have been found in the guts of deep-sea amphipods. Nowhere in the ocean is untouched by human activity. The deep sea needs protection. It's the largest ecosystem on Earth, and we know so little about it. Destroying it before we've even explored it would be a tragedy. There are efforts underway to establish marine protected areas, to regulate deep sea mining, to reduce pollution. But it's a challenge. The ocean is vast, and governance is complex, with international waters beyond any nation's jurisdiction. The deep sea is Earth's final frontier, an alien world on our own planet, still largely unexplored, still full of mysteries. What we've learned so far suggests that the ocean's depths are far more complex, more diverse, and more important than we imagined. and there's so much more to discover. For now, let's imagine ascending slowly from the deep. We've been at Challenger Deep, or thereabouts, nearly 11 kilometers down, in the cold and darkness, in pressure that would crush almost anything. Now, we're rising, slowly, gently. As we ascend, the pressure gradually lessens. The water around us, while still dark, begins to feel less oppressive. We pass through the hadal zone, entering the abyssal zone. The seafloor drops away below us, flat and featureless, covered in fine sediment. We rise through the midnight zone. Occasionally, a bioluminescent creature drifts past. A jellyfish, glowing faintly, trailing tentacles. A lanternfish, its light organs arranged like constellations along its flanks. At 1,000 meters, we enter the twilight zone. There's a faint glow above now, the first hints of sunlight, diffuse and blue. Barely perceptible, but there. Life becomes more abundant. Schools of fish drift past. Squid dart through the water, their movements quick and precise. We're approaching the zone where the daily migration begins. The largest movement of animals on Earth, happening every day, unseen. At 200 meters, light increases noticeably. We can see shapes now, colors beginning to emerge. First blue and green, then, as we rise higher, yellows, and finally reds. At 100 meters, the water is bright. Sunlight filters down, illuminating particles of plankton, schools of fish, the kelp swaying in the current if we're near a coast. And then we break the surface. Air, sky, clouds, the sun, bright and warm. We've returned from another world. A world of darkness and cold, of pressure and strange life, of mysteries still unsolved. A world that covers most of our planet, that holds most of its habitable volume, yet remains largely unexplored. It's humbling to realize how little we know about our own planet. We've been to the moon. We've sent robots to Mars. But we've barely scratched the surface of the ocean's depths. And perhaps that's fitting. Perhaps some mysteries should remain, at least for a while longer. Perhaps the ocean should keep some of its secrets. Beneath us, the ocean descends into darkness. Miles of water between the surface and the seafloor, between the known and the unknown. The planet holds more wonders than we can imagine. Places we've never seen, creatures we've never met, ecosystems we've never studied. The ocean is vast, and it's patient. It keeps its secrets well. Good night.